For a topic that's so popular with drawing tablets, it's surprising. We don't really know that much at all about how pressure works with drawing tablets. All we really have to go on is what the manufacturers tell us. And they tell us precious little. We might hear about the number of pressure levels, that's a popular topic, or lately they'll talk about the initial activation force. But usually, what we encounter are vague marketing claims about pressure sensitivity. In this multi-episode video series, I'll explore drawing tablet pressure. There are a lot of topics to cover. So if you have specific things you'd like me to explore, or you just have questions, please put them in the comments. Episode 1 is all about the fundamentals. How pressure is detected, how pressure information gets to your computer, and how your drawing application uses pressure to draw a brushstroke. Everything I'm talking about in these videos is about EMR drawing tablets, and so I'm not covering other technologies like AES, MPP, or Apple Pencil. And what I'm saying may not apply to those technologies. I did a deep dive into EMR technology back in 2022. In that video, I described a very primitive, early way that EMR pens detect pressure. Wacom hasn't used that method in decades. In this video, I will describe a more modern way that pressure is detected, and I'll clarify a few points from that older EMR video. The first thing we need to realize is, and this may come as a shock to some of you, it is not the drawing tablet which senses pressure. It's actually the pen. You can verify this yourself. Put the pen within about 10 millimeters from the tablet so that the tablet can detect that the pen is hovering. And then with your finger, just press the nib. You'll see that the drawing tablet thinks you're pressing down on the tablet. This is the Wacom KP501E pen, also known as the Wacom Grip pen. I'm going to break this pen down. This diagram will serve as a roadmap for what we are going to see. It doesn't include every component, but the key elements of pressure detection are there. First, there is the inductor that has two pieces, this coil of copper wire wrapped around a ferrite core, which is hollow. The inductor does two things. It's how the pen gets power from the tablet, and then it's how the pen, by transmitting an electromagnetic signal, communicates to the tablet. Then we have the nib and the pressure sensor. Remember, the ferrite core is hollow, and the nib goes all the way through that ferrite core to touch the pressure sensor. In reality, I've left out a couple of components here that are between the nib and the pressure sensor. For example, there's a spring to push back against the nib, and there's also a piece of rubber between the nib and the pressure sensor. Then we have the printed circuit board, the PCB. This contains a chip, which is the digital brains of the pen. Wacom pens have had a chip in them for a long time, but it's a very new thing for brands such as Huion and XP Pen. Another thing that is not shown in this diagram is some wires that I've left out. There are wires that connect the coil to the PCB, and there are some wires that connect the pressure sensor to the PCB. Here's that Wacom Grip pen broken down into those component pieces. You can see many of the things that I showed in the diagram. However, you cannot see the chip on the PCB. But in this photo, which is the other side of the PCB, the chip is quite clearly visible. You can also see the two buttons. On the left end of this pen is where you'd see the nib and the inductor and some of those other components like the pressure sensor. But I've removed them. But you can see an inductor, a coil, and a ferrite core on the right side of the PCB. That's actually for the eraser. This is a close-up of the pressure sensor. It's very small, having maybe a diameter of 2 millimeters. The front and back sides look very different. One side has some interesting sort of colors, but I can't remember which side was actually facing towards the nib. A modern EMR pen design is called passive EMR. Passive means that the pen does not have a battery in it. Instead, the pen gets its power from the tablet. What happens is, many times a second, the tablet is switching back and forth between two modes. In one mode, this grid of wires, which is the EMR sensor or the digitizer, is sending energy to the pen. And in the other mode, the tablet is listening for the pen. Now that the pen has a little bit of energy, it will send an electromagnetic signal back to the tablet, which is then detected. The frequency of this signal is called the resonant frequency. Why it has that name is discussed in that EMR video. Different pen models have different resonant frequencies. I don't know the resonant frequency for the Wacom grip pen, but I found a channel called ScanLime, and there's a video which describes the resonant frequency used by the Wacom CTH661 tablet. That resonant frequency was described as 750 kilohertz. So the signal is just this electromagnetic wave propagating from the pen to the tablet. Let's start with just thinking about this like a simple analog wave. By analog, what I mean is there is no digital information encoded in it. It's just a simple electromagnetic signal that has a frequency. And just with that signal, the tablet can tell some interesting things about the pen. The wires of the digitizer inside the tablet register that signal. And of course, the signal is strongest toward the middle and weaker toward the edges. And then, by taking a look at the signals across the horizontal and vertical wires, the tablet can estimate the position of the pen with great accuracy. The overall strength of the signal can also be used to estimate how far the pen is from the tablet. In other words, the signal strength corresponds to the hover distance of the pen. We tend to think about the tablet as getting an XY position of the pen, but actually, the tablet is sensing a three-dimensional position because it has this distance. If the pen is perpendicular to the tablet, then you will get a very symmetric signal. But let's say you tilt the top of the pen towards the upper right part of the tablet. Then the shape changes. And actually, you don't see just one peak, you get kind of two peaks in the signal. So this is how a tablet determines which direction the tilt is coming from and how strong the tilt is. Buttons and pressure make things a little more complicated. In general, there are different ways you can transmit information in a signal. Some techniques are analog. A typical analog way of changing a signal is to change the frequency, and some techniques are digital, in which case the signals are changed in some other way to encode bits of information, ones and zeros, which are then encoded in the signal and then decoded on the tablet. And both techniques are used depending on which tablet and pen you're using. To send button and pressure information in an analog way, most often we see that pens just alter the frequency of the signal. So, when pressing a button, for the duration of a button press, the signal will be altered. For pressure, because there's a range of pressures, then there will be a range of different frequencies used. In this case, for example, a lower frequency in that range means lower pressure, and a higher frequency in that range would mean a higher pressure. On the ScanLime channel that I mentioned earlier, I found some information on the exact frequencies used for a specific Huion tablet and a specific Huion pen. Keep in mind, these are very old Huion tablets. The resonant frequency is 255 kilohertz. If you're applying pressure, the frequency will change from 255 kilohertz to 266 kilohertz. And the two buttons use two different frequencies, 235 kilohertz and 245 kilohertz. Remember, this is for a specific tablet and pen. Other combinations of tablets and pens may use different frequencies. One thing you may notice in some non-Wacom pens, if you're drawing a stroke, meaning there is some pressure you're applying, and you press a button at the same time, this will cause an interruption in the stroke. But now that we know how you might transmit information in an analog way for both pressure and button presses, we at least have a clue why this interruption might be happening. Now let's take a look at the digital technique. In this technique, we avoid changing the frequency entirely. Keep in mind, there are lots of ways to digitally encode information into these signals. One of them is called phase key shifting. As the wave goes up and down, we can shift the wave so that it sort of skips over part of its cycle. And every time it skips, it counts as a piece of information, so a bit. Remember, one of the Wacom pens I talked about had a resonant frequency of 750 kilohertz. So there are plenty of opportunities every second to send these bits of information. Now, we do not know if Wacom is literally using phase key shifting to encode data in their signal. It's just an example of one of the many techniques that one could use. The strength of these digital techniques is we can send all sorts of information, from button presses and pressure information, or maybe a pen ID or other things, but transmitting these different types of information will not conflict with each other. The disadvantage of this technique is that it requires a more complex pen and a more complex tablet to encode and decode this digital information. Most often, we hear about pressure in the sense of pressure levels. So, for example, these days people talk about 8,000 something pressure levels, or sometimes 16,000 pressure levels. Let's keep it simple for a moment and just pretend there are 10 levels of pressure. And regardless of whether it's analog or digital, let's just pretend that the pen is sending an actual number to the tablet. So if we have 10 levels of pressure, the pen is sending numbers between 0 and 9. 0 indicates no pressure, in other words, the pen is just hovering. 1 should correspond to the initial activation force, and the value of 9 should correspond to the maximum pressure. And by extension, if we have 8,192 levels of pressure, we will see a similar pattern. 0 means hover, 1 means the initial activation force, and 8,191 means maximum pressure. If you want to see these numbers and verify what I'm saying is true, just take a look at your tablet driver. They usually have some diagnostic tool. In this case, I use an XP Pen tablet, and I open the driver UI and I press down to maximize the pressure, and you can see the highest pressure value it showed me was 8,191. One subtle point: the pen is reporting the pressure reading as a dimensionless number. Dimensionless means it's just a number, like 5, 7, or 5,000. There's no dimension or unit assigned to the number. What this means is it's not reporting an actual amount of force. So we don't actually know how much physical pressure is being applied to the pen. The tablet just knows it's a number, which is either higher or lower compared to some other number. The relationship between these pressure readings and the actual amount of force is a topic we will explore in a future video. Now that we know what the pen is transmitting, let's talk about what logically must be happening inside the tablet. I say logically because we don't know what the tablet is actually doing because we do not have access to the source code of the firmware. Think of this as an educated guess. First, of course, the tablet has to detect the signal, and then it has to decode the signal. Decoding means it gets those values for position, hover distance, tilt, pressure, and button status. Then the tablet firmware may process this information. For example, it might perform some position smoothing, or it might perform some smoothing on the pressure values. In any case, the tablet is going to take all this information and send it to the computer in the form of a report. The report is just a collection of numbers, and it contains all the information you would expect: position, tilt, hover distance, pressure, and button status. Tablets send these reports many times a second to a computer. The number of reports per second will vary depending on which tablet you have. Wacom professional tablets tend to send about 200 reports per second. Here's another logical view of what happens to the report as it's received by the computer. The information will go through various layers, like the USB system and the human interface device layer, and whatever passes for a tablet subsystem. Eventually, that information will make its way to a driver. And the driver will take this information and it might also adjust it. So the driver might do position smoothing, or it might do pressure smoothing. And probably you're familiar that drivers will let you control the pressure curve. But all the things that a driver does is unknown, because this is another case where we do not have access to the source code for these manufacturer drivers. If you're interested in what a driver really does, then take a look at Open Tablet Driver, and you can find all the source code on GitHub. I mentioned that the driver might use a pressure curve. I will cover pressure curves in a future episode. Eventually, this report will reach a drawing application, and the drawing application will try to render a stroke. The component of a drawing application that takes that data and makes it into a stroke is called the brush engine. There are different brush engines that do different things, and they have wildly different levels of complexity. But here is a simple logical diagram of what a hypothetical brush engine would do. And I'm basing this roughly off what I see Krita do. The brush engine can take information from the tablet and apply it to different aspects of a stroke. For example, the opacity of a stroke, the stroke width, the color of the stroke, the brush angle, all sorts of things. In Krita, you can apply pressure information to different aspects of a brush simultaneously. For example, with the Ink 3 G pen, in Krita, by default, the pressure is linked to the size of the stroke, and it uses a specific sigmoid pressure curve by default. Sigmoid just means S-shaped. And here, I've customized that brush to take the pressure and also map it to opacity. And this means the heavier I press, the more opaque the stroke is, and the lighter I press, the more transparent. In this case, I have configured the brush to use a linear pressure curve. You may have noticed that there are actually several things that have the word pressure in them in the Krita settings for a brush. There's the pressure I've been talking about, then there's pressure LN, and then there's tangential pressure. So that may be another topic for a future video. Here, I've set Krita and its brush size to be 100 pixels. The brush engine will have to take that user-specified brush size, 100 pixels, and combine it somehow with the pressure data to get the actual size of the stroke to vary as I press lighter or harder. At least for this brush, it's actually pretty simple to understand how this would be done. We can start by realizing that Krita has a setting called spacing for this brush, which is currently set to auto. But if we set the spacing to different values, you'll see that this stroke is actually rendered as a series of dabs. In this case, each dab is a circle. And this means that we now have a very clear clue about what to do with the pressure. We need to map it to the diameter of these circles. Here is some pseudocode to help you understand how this actually happens in an application, at least in principle. First, we have to get the user brush size. In this case, I'm setting it to 25. Second, we have to normalize the pressure. Different tablets have different numbers of pressure levels. So it's easiest for us to have a consistent way to handle all the cases. So we don't have to change our code if the tablet supports just 2,000 levels of pressure or 8,000 levels of pressure or 16,000 levels of pressure. We want one technique that works for all of them, and we do that by normalizing the pressure. What we do is we take the pressure reading, which is an integer that goes from 0 to, in this case, let's say 8,191, and then we transform it into a floating point number that goes from 0 to 1.0. To make this transformation is easy. We just divide the pressure reading we're getting by 8,191. Now that the pressure is normalized, it will make the math easier later on, and you'll see that in future videos. One point about this normalization, I've shown it here as something that is done in the application, but these days, I think the normalization is something that happens more often in the driver. In any case, it doesn't matter where it happens, only that it does happen. Now that we have normalized the pressure, a brush engine would adjust it based on the pressure curve. I am going to cover pressure curves in a future episode, so for now, assume that the pressure curve function doesn't do anything. It just returns the value it is given. So if we give it a value of 0.5, it will return 0.5. And to get the current brush size, we just multiplied the normalized pressure by the user-specified brush size. There's one last tweak here, which is I'm saying that the brush size is the maximum of either the number 1 or the brush size that we just calculated. And not all brush engines would do this exactly, but I'm showing this to you because it's interesting to understand again how pressure is used. The situation this is trying to deal with is, at really low pressure, when you calculate the brush size, you might get a number that's really, really small, much smaller than a pixel. And so in this case, you might want to make sure that at least one pixel is always drawn if there's any pressure, and that's what this last line accomplishes. Again, this is pseudocode. This is all conceptual. If you look at the source code for any drawing application, you will see something much more complex. We went through a lot of things in this video, and there are a lot of other things I want to cover, but I'll save that for future episodes. Thank you for your time, and I hope you enjoyed this video.